Welcome to your first look at AP Precalculus. In this introductory video, our goal is to understand the heart of this course, the study of functions through the lens of dynamic covariation. Let's look at our learning objectives. First, we will define a function and identify its domain and range. Second, we will understand functions as the covariation of two quantities. By the end of this session, you will be able to explain what a function is and how two quantities change together. This is a crucial step in preparing for calculus. To start, let's revisit the formal definition of a function. You've likely seen this in algebra, but in AP Precalculus, we look at it with a bit more depth. A function is a specific type of mathematical relation. It maps a set of input values, which we call the domain, to a set of output values, called the range. The key rule is that each input value is uniquely mapped to an output value. In other words, one input cannot lead to two different results. Imagine a machine. If you put in the number 2, and the machine is a squaring function, it must give you 4 every single time. If that same machine sometimes gave you a 5 for the same input of 2, it would no longer be a function. Now that we have the definition down, we can move on to seeing how these functions actually behave in the real world. In AP Precalculus, we don't just look at static equations, we focus on dynamic covariation. This is the idea that as one quantity changes, another quantity changes in response. Our goal here is to understand how the rate of change in one variable affects the other. Consider a plant growing over time. As the time quantity increases, the height quantity also changes. They covary. Notice that the height doesn't just jump from one value to another. It changes continuously as time passes. In calculus, you will look at how fast this change happens at a single moment. In precalculus, we prepare for that by studying the patterns of these changes across different types of functions. Understanding this movement is what separates precalculus from basic algebra. We are moving from what is the value to how is it changing. To truly master functions, we must be able to view them through 4 different lenses. 1. Graphical, 2. Numerical, 3. Analytical, and 4. Verbal. These are known as the multiple representations of functions. Each one reveals different attributes and is useful for solving different types of problems. Our goal is to move fluidly between graphs, tables, equations, and descriptions. Look at the analytical form, the equation f of x equals 2x plus 3. This is great for precise calculations. Now, look at the numerical table. It shows us specific data points, which is often how we collect information in science or business. The verbal description gives us the context, the story behind the numbers, starting at 3 and increasing by 2. And finally, the graphical representation allows us to see the overall trend and behavior at a glance. Throughout this course, you will practice translating a verbal scenario into an equation, or an equation into a graph. By mastering all 4, you'll be able to choose the best tool for any problem you encounter. One of the most powerful things about precalculus is its ability to model the world around us. We use function models to describe real-world data and predict future outcomes. To do this, we look for specific characteristics in the data. Suppose we are tracking the height of a ball thrown into the air. We collect data points showing time and height. We can create a mathematical model, an equation, that fits these points. We call this a model. The model tells us the maximum height the ball reaches. It also tells us exactly when the ball will hit the ground. We use these models for 2 main things. Interpolation is predicting a value between data points we already have. Extrapolation is predicting a value outside our data range, like where the ball will be 2 seconds after our last measurement. However, remember that every model has limits. Our ball model might assume there is no air resistance. In the real world, if a strong wind blows, our model becomes less accurate. As you move through this course, you will learn that choosing the right function type, like polynomial or exponential, is the first step in building a good model. Now that we've covered the conceptual foundations, let's look at the map of the specific functions you will master in this course. Our journey includes polynomial and rational functions, exponential and logarithmic functions, trigonometric and polar functions, and finally, functions involving parameters, vectors, and matrices. In the first part of the course, we focus on polynomial and rational functions. These are built from simple power terms like x squared or x cubed. They are the workhorses of algebraic modeling. Next, we move into the world of growth and decay with exponential and logarithmic functions. If you've ever heard of compound interest or population growth, you've seen these in action. They help us model quantities that change at a rate proportional to their current value. Then, we dive into trigonometry. We explore periodic behavior, things that repeat, like the tides, sound waves, or the rotation of a wheel. We also extend this into polar coordinates, where we locate points using a distance and an angle rather than just left-right and up-down. Finally, we look at more advanced ways to define relationships, using parameters, vectors, and matrices. These tools are essential for modern data science and physics. Each of these topics builds on the rule of 4 we discussed earlier. You won't just solve for x, you'll learn how these functions move, grow, and interact. Before we dive into new topics, it is vital to ensure your algebraic foundation is rock solid. AP Precalculus builds directly on your work in algebra and geometry. Let's look at why these matter. In this course, we often need to find the zeros of a function to understand its behavior. If you are given a quadratic function, like x squared minus 5x plus 6, you need to be able to factor it quickly. By factoring this into x minus 2 times x minus 3, you find that the function crosses the axis at 2 and 3. Similarly, when we study exponential functions, you'll need to remember your exponent rules fluently. If you have x to the power of a times x to the power of b, you add the exponents. Take a moment to look at this list. If any of these feel rusty, spending a little time reviewing them now will make the upcoming chapters much smoother. Mastering these basics allows you to focus on the new, complex concepts of covariation rather than getting stuck on the arithmetic. In this course, technology isn't just for checking your homework. It's a tool for exploration. We use it for graphing and analyzing, generating tables, finding zeros and extrema, and performing complex calculations. Our objective is to learn to use technology to deepen our conceptual understanding. Let's see how a graphing utility helps us understand a complex function that would be difficult to draw by hand. Suppose we have a fourth-degree polynomial. By graphing it, we can immediately see its overall shape. Using your calculator or software, you can precisely locate the minimum points or valleys of the graph. This would be very difficult to do with just pen and paper. We can also generate a table of values. This numerical view helps us see the rate of change. Notice how as x increases from -1 to 0, the function value jumps up, but then starts to decrease as x goes from 0 to 1. Finally, technology allows us to find zeros, the exact points where the function hits the horizontal axis, even when the numbers aren't clean integers. By offloading the tedious calculations to technology, we can spend more time thinking about what the results actually mean for the situation we are modeling. To wrap up our introduction, let's synthesize everything we've discussed by looking at a real-world scenario. This will show you how covariation, representations, and modeling all come together. Imagine you are a data scientist tracking the spread of a new social media trend. The number of shares starts small, then doubles every hour. We can represent this analytically with an exponential function, where s is the number of shares and t is time in hours. Numerically, we see the output values doubling. Notice the covariation. As time increases by equal steps, the number of shares increases by a factor of 2. This is a specific pattern of change. Graphically, this looks like a curve that gets steeper and steeper. The rate of change is not constant, it is increasing. If we want to predict how many shares there will be in 10 hours, we use the model to extrapolate. But wait, what are the limitations? Will it grow forever? Probably not. Eventually, everyone who is interested will have seen it. The model will need to change to reflect that. This is exactly what you will be doing throughout AP Precalculus, taking a situation, finding the math that describes it, and using that math to understand the world. We have covered a lot of ground in this introduction to AP Precalculus. Let's take a final look at what we've established. First, we established that functions are unique mappings. Then, we looked at covariation, which is the heart of dynamic change. We introduced the rule of 4, graphs, tables, equations, and words. And finally, modeling, using math to predict and describe. You've seen that this course is more than just a collection of formulas. It is a coherent capstone experience designed to prepare you for the rigors of calculus and beyond. This includes understanding rates of change, analyzing continuous movement, and mastering complex function behaviors. By focusing on how quantities change together, that dynamic covariation, you are building the conceptual bridge to derivatives and integrals. As for your next steps, review your algebra foundations, get comfortable with your graphing technology, and prepare to look at the world through the lens of functions. In our next lesson, we will begin our deep dive into polynomial and rational functions, exploring their zeros, intercepts, and end behaviors. We have successfully introduced the purpose, scope, and key themes of the AP Precalculus course. Take some time to reflect on the rule of 4. The next time you see a graph or a data table in the news or a science class, ask yourself, how are these quantities covarying, and what would the equation look like? I'll see you in the next session.